Hi, welcome to the third video on the introduction to the simple manipulator control library used for all the control of robotic manipulators. In this video, we'll be going over the Pinocchio library that I heavily rely on within my library to do all of the standard sort of computation for robotics, things like forwardKinematics, things like this. And because I rely it so much, I have the need to introduce it really quickly, as I did everything else. Yes, let's start. Okay, so in this short video presentation, we will be going over three things. Number one will be Pinocchio itself. And I will cover everything you need to know about Pinocchio to use the library that I wrote within the first section, okay? So you don't need to go over the other two parts. However, as you might have noticed throughout these tutorials, if you've been watching it from the beginning, I can't help myself. I need to give you I need to scratch beneath the surface to see that there's a lot of things going on below, so that you don't have the sort of let's say false sense of security that, you know, because you went through these speed runs that's sort of it. Now, it is it depending on your application, on your use case, and how you know, if you just want to get a taste. However, for those who get a taste, say, man, this is pretty good, I want to know more, I want to provide them with the option of knowing where to go next. This is the goal. So, as it was so far, it is in this presentation as well. Okay, now let's start with Pinocchio. So, I will show these parts in code so that we remain incredibly pragmatic and focused. At the end, I will provide you more documentation on Pinocchio. I just want to say it's a phenomenal project. I thoroughly enjoy it. I use it. It's a phenomenal project. Okay, but let's start immediately by going into the code. Now again, I will be in my native installation simply because I don't want the text to be bolded, same as in last video. But you can view the exact same things on the Docker image you have installed. Okay, now we can do this a bit prettier. Now I'm in the Python directory, and the simplest way for me to go and find things is to start with something and then just click to with GDF. If you're following along, you have this as well available in the Docker. So I just type GDF, that's it. I don't want to have the screen key below because I don't want this to be focused on Vim commands and have a lot of like moving stuff on the screen. Now I wanted to, yes, well, the simplest way to find all this is to just search for the keyword pin. That's how I'll get to everything. Now I want to find something with data and model. I use it, I put it in self.data in the robot manager. Okay, so Pinocchio. In Pinocchio, you put in your robot model. We will be loading it from urdf. I will very briefly show this as well. But if you're just working on the UR5 robot, this is sort of predefined. And really, if you have a well-defined urdf model, you don't have to think about this pretty much at all. But once you have the model, the information about the model will be given in this model class. Do we have some documentation for that? No, we would have to go to Pinocchio to learn more. I will simply shortly explain what do we have here. Let's see if I get some, yeah. Okay, so model is all the static information about the model that you have, plus some sort of functions that go with it. So we split the big robot class, let's say, into model and data. Model is where the static things live. Data will be where the things that change live. Okay, so here we have the options to, you know, add a joint, see all the children if there are some, get information about the frames, so they're static. So the, you know, if you have something like the Denavit-Hartenberg convention or whatever, then you know that there are these different frames that you set in the beginning with all of the joint positions being 0 or whatever to get the kinematic structure of the model. So that would be there. We have set things that don't change, like gravity. We have some basic information like the number of joints, the number of envy is something I will introduce later. And yeah, that's kind of that. And now in the data, we have the things that change. So that would be our joint positions, velocities, accelerations, and so on. By default, it has all the dynamic information as well. If you don't use dynamics, as this my library currently doesn't, then these will simply be left as initialized. Out of the things that are of particular interest would be the OMI. That will be the body placement with respect to the world. So if you, in this list, select your end effector joint, you will get the position of the end effector joint. You need to call forwardKinematics first. And of course we have, yeah, you know, the standard things like velocities. I just, you know, this is named in a particular way. If you look at Pinocchio documentation, it will make perfect sense, but I just wanted to outline it in the beginning. All right, so that's it on that front. And I can see that I don't need to shrink my face yet. Not for this anyway. Okay, loading the urdf. Now I have sort of a small wrapper function get model here. But essentially, we just have the urdf that's defined. You know, you can search for what the urdf is, a universal robot description file, and typically you just want to download this for a particular industrial robot that you have. You can of course create your own for your own robot, but it's a ugly XML file that does exactly what you think it does, and yeah, hopefully you don't have to edit it ever. Okay, and here I put in the particular calibration for my robot, the particular one we have in the lab. Okay, and then with this, yes, you give it the path. It builds the model, the visual and the collision model we don't really use. I mean, we use visual model to pass it to Meshcat to get visualization. The collision model is kind of is the model you would use if you wanted to define things like self-collision with HPP FCL. That's sort of the within this Pinocchio universe. That's the library that you would use to detect contact, basically, and if things overlap or not. We're not using this at the moment, so doesn't matter, and that's it. Then we create the data from the model, and that would be it. So very simple. Next we have forwardKinematics. Do have it forwardKinematics? Yes. So you basically pass it the cues that you have, joint positions. You could, for whatever reason, yeah, if you're doing dynamics, then I guess you would want to have the velocities, the acceleration as well in the code. For velocity controlled robots, you won't need this, so you would just pass some zeros over there. And what that would do, as pretty much every Pinocchio operation, is it would update the things that need to be updated in the data. And in this case, we're just getting the end effector position, so we find the OMI, and then we have the joint ID, and that's it. Okay. Right. Okay, who cares about this? Let's keep going. CalculateJacobian. Now I don't have this actually in this file. Maybe I should. In any event, if you're doing I forgot where I am. Classic. It's easiest just to exit and open it again. If we go to the control loop for closed loop inverse kinematics, you will find that I call this Pinocchio.computeJoinedJacobian function. Now I'm sort of torn between whether I should obfuscate Pinocchio in my wrapper or expose it. I am not really sure what's the best. Now we have the worst solution, which is something in between. But essentially, yeah, okay. That's if you want the joint Jacobian, you pass the model, the current joint positions, the data, and that's it. And if you want it for a particular joint, you would pass this. There's, I think in data, there's a line where all of them are saved somewhere. Anyway, this is what to use if you want the Jacobian. On this note, there's something incredibly important I need to discuss. So all of these functions look simple, and they are, but you have to be aware of something, which is it's actually, yeah, I do want to show this here. So should have cut this. I apologize. I need to speed run through these videos. So bear with me. If you want to define an error in Cartesian space between the current position and something else, okay, and then compute the velocity vector that would in one unit of time bring you from here to here, this velocity vector will be by default defined in the body frame of the end effector. Okay, now this is connected to the concepts of body and space frames and body and space velocities. I'll make my face a bit bigger because I want to use my hands to explain this. Right. So if there's some space frame that doesn't move, it's in the corner of the room, like this, but imagine it's in the corner of the room, and we say we have a velocity of going forward like this, and we have some sort of a rotational velocity as well, but it's defined in this frame. Then the object here, this coordinate frame, would move like this. Okay, this is what you expect, because these quantities, every dimension of the velocity is decoupled. So if you have zeros, and in this vector direction you have some number, and the angular velocity around this axis is some number, everything else is zero, then you would have this. Now, if you have, then typically we use the, for expressions for understanding things, this is the frame we use. That would be in the base of the robot typically. However, if you have the body frame, then in this frame, that's the one that is moving, that's where you would have your velocity defined. Now let's say again that we're moving in this direction, and there's an angular velocity around this axis. Then one what is it called? One infinitesimal step later, we moved in this direction and we rotated as well. The next one moved again and rotated about here, because again, in this frame is where the velocity is defined. So you would have motion that looks like this. Okay, so the vector of velocities looks the same. They're both in Cartesian space, but they're different. Now, Pinocchio sometimes by default gives you the velocities in this frame, particularly when you want to compute the difference from some frame to another frame, and you want to the homogeneous transformation from this to that, and then you want to turn this into a velocity, then you would that would be in the body frame. Okay, let's get back to the presentation. Now, in order to, okay, so Pinocchio uses Lie algebra, Lie group mathematical terminology And I will get into this in the later portion of the video. But I will just sort of, you know, if you don't care, that's totally fine. You can just use this code as given, and I'll explain what it does really quickly. So you have your current position of the end effector. You want it to get somewhere else, to your goal, to your task. Oh no, sorry, this is the goal. And this right here is your joint, your end effector position in the base frame. If you then do an inverse action on this, which basically what this does is it gives you this transformation from your current position of the end effector to the goal. Okay, this is a homogeneous transformation matrix. Now we can turn this homogeneous transformation matrix into a vector of velocities, Cartesian velocities given in the body frame, like I just went over. And now with this error vector, you can use this error vector to compute, if you're doing closed loop inverse kinematics, the joint position, the joint velocities that would act so that the end effector moves in this error vector. Okay. If you just use the code as given, you don't need to think about this ever, but since it looks weird, and it, you know, the explanation for it is a bit involved, I will be including this explanation shortly. But yeah, again, if you want to take it as it is for granted, that's totally fine. Okay, and now let's look into the cheat sheet that Pinocchio offers, just so that you have an idea for what's out there. Let me put my face down. Software Pinocchio. I could have had it open already. PDF, not the paper, but the cheat sheet. Okay. Pinocchio documents. Okay. So in the here we have all of the different math. Again, it uses the Lie algebra formulation for robotics, but all of this is implemented. We have something a bit about what's in the model. We discussed this already. We have information on all the various frames that are pre-computed and how to access them and which ones get updated how. Of course, you have this in the online documentation as well, but it's the easiest to see what exists in the cheat sheet. Here's something for the collisions. We have some sort of predefined configurations, the calculation of energy and so on. This is what you want to use for kinematics, different ways to get the Jacobian. And we have the, if you're doing dynamics, all of these functions exist here as well. Okay. That's everything I want to show, just so that you know what categories of functions exist. Okay. I will show the documentation and tutorials at the end in order to bait you a bit into watching the rest of the video.